Okay, we are in energetics of locomotion. And in particular, really focused in on running. I'm not going to do walking at this point. There are some differences between energetics of locomotion for walking and running, and skipping and hopping, and all different forms of locomotion. And because there are differences, I'm going to zero in on running. Now, this is a nice discussion that blends physiology and mechanics, and even motor control or motor coordination. So I always like to start this conversation by thinking about just going for a run. Well, what's interesting is if you just go off for a run, you're going to you're going to pick a particular running style for some reason. And what's also interesting is it's pretty easy to pick out your style if you know a runner. For example, let's say you've got a friend who runs with you, and you see that friend off in the distance, but you can't see their facial features, but you can see their running style. You can typically say, "Oh, I know who that is. That's so and so," because you're looking and seeing their running style, and you're recognizing that pattern as unique to that person. Well, likewise, we all have general similarities in running. We have a stance phase, a swing phase, one foot's in contact with the ground, things like that. But there's also very unique aspects of our running style that we select. And I've always been interested in why we run the way we run. And obviously, there's no answer to that, but at least not yet. It's very multifactorial. And we've done a lot of work in our lab trying to tease out things that may drive or may not influence why we run the way we run. But I've used this term running style. All right, I'm putting it in quotes because sometimes when we put things in quotes, it means, oh, we have a hard time defining it. Well, what are the basic kinematic descriptors of locomotion are stride rate and stride length. These are the basic kinematic descriptors. Now, let's just define these. Stride rate is how fast we're taking strides. Are happening, how fast strides are happening. And stride length is how far of a distance is covered with each stride. Now, it's important to define a stride because the literature is really mixed bag with some definitions. And so let me try to draw a picture of a person running here. Okay. Here's a person at some time, and this is, let's say this is the right foot contact. Well, sometime later, this left foot is going to come and contact the ground. I'll do this continuous, so the person's running over ground. And I'll draw that. It's actually not too hard. I'll just try to draw it the same way. Okay. But now this is the left foot. Okay. And then at some moment later in time, I'll try to draw the same picture a third time, but it's not the same picture. It's just a person further along. And now this would be the right side. A stride is one side to the same, it's some discrete event to the same discrete event on the same side, very next contact. Or so I'm stumbling a little bit because here I'm drawing this as a contact to a contact. That would be a discrete event would be contact. We could also define a stride based upon toe off to toe off or mid stance to mid stance. There's lots of different ways to actually define the start of a stride and an end of a stride. But using contact to contact is an easy one to sort of zero in on. this would be a stride. And stride rate is how fast we're taking those strides. And stride length would be the measure of distance from here to here. The one side to the other side is a step. Okay. Now there you have step rate, you have step length. When you're reading this literature, you need to be really careful about how the authors are defining stride and step. There is a lot of mixture of these two terms, unfortunately. And there are different ways to represent these two terms other than what I've done here, but in essence, they all come back to how fast strides are happening, how fast something is repeating, and then how far we're traveling for each stride or for each step. Okay, so let me get the piece. So stride rate has units of strides per time. And I'm going to put strides per minute here. That's very common to see that. Another set of units that are used are strides per second. And when we see stride per second, we'll see units of hertz. So if you're reading the literature and you see, oh, the stride rate was 1.2 hertz, well, just realize that's 1.2 strides per second. Hertz is almost anything over seconds. Strides per minute, we'll typically talk about 80 strides per minute or 90 strides per minute, something like that. And then stride length is how far we're covering a distance per stride. So it would be meters per stride, for example. All right. So now here's what's really interesting is if we take the product of stride rate times stride length, we actually get running velocity. If I just look at my units, that bears itself out here. Stride rate, I'll use strides per second just as my choice of units here. And I'll use meters per stride for stride length. And you'll see the strides get canceled and I'm left with units of meters per second, which are units for velocity. All right, so I go through this basic overview of running kinematics and running style because there's a lot of neat work manipulating either stride rate, stride length, or velocity, and then understanding or measuring some parameter, ground reaction forces, angles of movement about different joints, even physiology. All right, so one concept that I like to really tie in with the energetics of locomotion in running style is the physiology. I do this also in physiology of endurance performance. It's that important to really understand this basic experiment, which really drives a lot of different experiments and understanding of the importance of our preferred running style. So I'm going to describe here an experiment where I'm going to put stride frequency on the x-axis. All right. So this would be a low stride frequency. This would be a high stride frequency. And then we would have some other stride frequencies in here. So this would be a low and this would be high. I'll put numbers down later. All right. And over here, I'm going to put VO2, and I'm going to put the dot here. And now hopefully you're starting to recognize the importance of that dot because this is a rate. So milliliters of per kilogram body mass per minute. Okay, typical set of units. So if I bring you in and I bring you into the lab and I hook you up to an instrument to measure VO2, and then I put you on the treadmill and I set the speed to some speed. All right, I pick the speed for you. Maybe I'm picking 8 miles per hour. Okay, so I'm going to write that here. Speed set at 8 miles per hour. Okay, it's not terribly fast, but it's a pretty good pace. Okay, 8 miles every hour. All right, and I say, okay, just go ahead and start running. And I'm going to measure your VO2 while you run at that 8 miles per hour. I'm measuring your rate of oxygen consumption. And what's interesting is you're going to pick a particular stride frequency, and I'm going to call that PSF, preferred stride frequency. Okay, that's what that's going to be. Sometimes we call it self-selected stride frequency, but it's whatever is preferred. And you're going to pick a rate that's pretty consistent over time, especially for that speed right there. All right, and again, I got you hooked up to my metabolic equipment, and I'm measuring your VO2 for running that speed using that stride frequency. And it's not much, whatever that is, okay? It's some number, maybe it's 30 mLs per kg per minute, doesn't matter. All right, so now I'm going to continue this experiment. You're running at 8 miles per hour, but now I'm going to tell you to run with a 10% faster stride frequency. All right, so if you're running 80 strides per minute, now you're going to run 88 strides per minute. So faster stride frequency, or, oh, I'm sorry, I do this all the time, and I apologize. I don't like to be inconsistent with my terms, but stride rate and stride frequency are the exact same thing. And I just get lazy and I do bounce between the two of these. Sorry about that. Okay, so now you're going to run 88 strides per minute. So I'm going to put plus 10%. So this is faster. So you're running the same speed at a faster stride rate. So what's going to happen to your stride length? Your stride length is going to get shorter. So now you're taking smaller steps, smaller strides, but you're taking them at a faster rate. And I'm measuring your VO2. What's interesting is your VO2 will be greater. And now let's do that again, but now I'm going to have you run at 20% faster stride frequency or faster stride rate. So now what's going to happen to your stride length? You're still running 8 miles per hour. So knowing that stride rate and stride length is the product of those two is your running velocity. If this is constant, if I'm increasing stride rate or stride frequency even higher, then my stride length has to get even shorter. And interesting enough, my VO2 will go up. Okay, now I'll bring you back. We'll run at your preferred. And now what I'm going to do is go in the other direction. I'm going to say, okay, I want you to take slower strides. So we're going to go less than 10% slower stride rate. So if you were at 80 strides per minute, you're now going to run 72 strides per minute. So what does that mean to stride length? It means your stride length is going to be longer. And interestingly enough, your VO2 will go up. I'm going to do that again at an even slower stride rate, stride frequency, and your VO2 is going to go up even more. And this is a very common expected data set, where if I connect those dots roughly, okay, I'll get what's called a U-shaped phenomenon. Sometimes we call it a J-shape because this side may actually increase faster than this side. So it would be a J, that's a J. So, but in essence, we call this, we refer to this as a U-shaped phenomena. And a lot of times, I know a lot of people like to use words like optimal. Well, optimal means finding the lowest rate of oxygen consumption to run at this speed, which happens to be right at PSF, or it's going to be really close to PSF. Sometimes we test runners out and maybe their PSF is off in one direction or the other relative to the minimum of this U-shaped phenomenon. All right. And then the tendency is to say, from a coaching perspective, well, maybe we want to push that athlete more closer to where the minimum VO2 would occur across these ranges of stride frequencies. And there's a lot of discussion. It continues to be discussed whether or not that's the right way to go. But what's really interesting here is this is a big change. If you run, change this, and you try to if you try to change your stride rate from 80 strides to 88 strides per minute, you really got to focus in on that. And if you don't continue to focus on it, what will happen is you may start at a faster stride rate, but then over time, you'll slowly move back to your preferred or something close to your preferred stride rate. All right. Really interesting to see that happen. So that brings in, that's why I mentioned this is almost like a biomechanics, physiology, motor coordination issue, is that motor control of your gait can be really hard to change, that you still want to keep coming back to your preferred stride pattern. Why? Well, maybe it has something to do with VO2, but at the end of the day, it probably doesn't. All right. Uh, and the reason is that this change in VO2 in plus or minus 10%, sometimes when we just look at what happens within this window, we don't see a big change. Maybe this is 1 to 2 mLs per kg per minute. All right. Not a lot. Now it's going to be partly speed dependent because remember, this is running at 8 miles per hour. Maybe if I go faster, maybe it'll have a little bigger change. And you'll see in a presentation that I have associated with this work, you'll see that we actually looked at that experiment, or what happens when you change speed and what happens to this relationship. It actually was opposite than what we thought, but you can watch that presentation, get a sense of what happened there. But at the end of the day, this 1 to 2 mLs per kg per minute over plus or minus 10% change in stride frequency is not, it's not a huge amount of change in VO2. And in reality, trying to change your VO2 even plus or minus 5% is trying to change your stride frequency or stride rate plus or minus 5% takes a lot of conscious effort to do so. And so there's probably not a lot of negative influence into small changes in stride rate. So what drives preferred stride frequency is sort of a conceptual question. Again, the question I like to just reduce this as is, why do we run the way we run? And so this is one big reason is something to do with physiology, but we actually find that we have probably some good slop in the system that allows us to change stride frequency a reasonable amount and not have a negative influence on VO2. Increases in VO2 would be a negative influence, meaning I need to convert more calories at a faster rate for the same speed if I'm using a less efficient running style. Okay. I'm drawing a blank on what I was going to say next, but yeah. So what drives stride frequency? It has something to do, but this is not the complete answer. And we need to continue to look at what is going on with changes in stride frequency, or why that preferred stride frequency is so important. Oh, that's what I was going to say. Is what's really interesting here is, as I mentioned, it's hard to change stride frequency in this type of experiment. But if I have you run on sand or in the water, oddly enough, because we do a lot of that work, or on grass, or on a track, or in snow, or if we start changing certain conditions that you're running in, maybe different running shoes, what's really interesting, you can adjust that PSF so quickly without even thinking about it. So running in snow, you'll change your preferred stride frequency pretty quickly. Even running on bare feet, you'll probably change your preferred stride frequency really quickly. But if I try to force you into a change for whatever condition that you're running, it's really hard to get you to choose a different running style, which leads to some really interesting experiments. And some of the work that we've done with running a body weight support, running in the water, running with different shoes, running fatigue, all those are getting at trying to understand why you may or may not be changing running style, what's happening mechanically, and what's happening physiologically. Okay, so energetics locomotion, part two, I'm just trying to tie in the mechanics, in this case, running style, and using right now just the basic kinematic descriptors of running style and looking at seeing how that influences physiology and how motor control is ultimately tied within here. So to understand energetics of locomotion, you got to know physiology, biomechanics, and motor control. All right, that's it for part two.